So now here is a okay. So motional EMF. So in this thing, you have a magnetic field into the plane of the paper. Okay. And so in the presence of this magnetic field, so let's say you take a metal rod and move it perpendicular to the magnetic field. Okay. So if you move it perpendicular to the magnetic field in the metal rod, there are free charges, and the charges are moving in the presence of a magnetic field, so they feel a force. So for instance, negative charges will feel a force in this direction, they'll collect over there. Positive charges will collect over there. Well, what really happens is negative charges in a metal, the free charges are electrons, so they'll collect over here, and this leaves a net positive charge there. Okay, and they will keep moving till what happens is, so when the charges separate, so let's go to the board. So you have a magnetic field like this. You take a metal rod and you move it in this direction. And what will happen is negative charges will collect here. Okay, so if you have a positive charge, I'm going to do this on the side. If you have a positive charge moving like that, or we'll do a negative charge. Moving in this direction, force is Q V cross B. Okay, and use your right hand rule. So V cross B, you turn from the first vector to the second vector, V cross B. On a positive charge, the force would be in the upward direction. Okay, and on a negative charge, the force is in the downward direction. So the force will be in this direction, and you see a bunch of negative charges will collect here. Okay, and induced a voltage here. Okay, and this voltage or EMF is equal to the magnetic field times the length of the conductor times the velocity at which it's moved. Okay, so that is motional EMF. Okay, so you take a conductor, again, just take a piece of metal, and in the presence of a magnetic field, if you move it, you induce a voltage in the conductor. Okay. Now this won't happen if velocity is parallel to the magnetic field. This is for velocity perpendicular to the magnetic field. And so if you have a velocity that's at an angle, the component parallel to the magnetic field will not do anything. It's only the component perpendicular to the magnetic field that'll give you the induced EMF. All right, well, how long do the charges separate? Till the electric force equals the magnetic force. Okay, that's what that diagram is telling you. And that's what this shows you. The electric force is equal to the magnetic force. And the induced EMF is the Q cancels. The induced EMF, the voltage between the ends of the rod is the electric field times the length of the rod. And there's the expression, B times L times V. All right, so again, so in this diagram, what this is showing you is, so right now, so there's the magnetic field, here's the rod, and you move the rod in the presence of that magnetic field, you induce a voltage at at the end of this rod. And the voltage is B times BLV. The negative sign again is related to the direction of the current induced. Okay, so you induced a voltage in this rod. Okay, now that voltage will drive a current. It'll drive a current like this. Okay, so without any batteries, you're passing a current through this wire. Okay, just like in the previous examples. Okay. So it seems like you're getting free energy out of it. Free electrical energy. Imagine the following. Here's a frictionless railing. Get the rod moving at constant velocity. And if you let go, if the rod keeps moving at constant velocity, there's free current, free electrical energy. What gives? Did you guys understand the question? So it turns out that when there's a current flowing through this thing, there's a magnetic force that comes into play. So the magnetic force on the current carrying conductor is in this direction. So if you want to maintain that velocity, you have to keep applying a force to oppose this magnetic force. So like we said, like we keep saying, there's never ever free lunch. So to keep this rod moving, you're applying a force, and that is what's producing the electric current. So anyway, this is again a transformer. Whatever energy you use to apply that force to do that work is being converted to electrical energy. Okay, so this device is another transformer. Okay. Okay, and so this slide shows you can look at it, and the motional EMF as a consequence of Faraday's law. This is showing you the EMF is time rate of change of flux, and the flux is, as the area is increasing, the flux through this loop is changing, and d by dt, the flux is the magnetic field times the length of the rod times x, which is the area of the loop, and it's x that is changing, the x that is changing. So that's dx by dt is the velocity. All right, so here, let's see, where's the motional EMF simulation? Oops. All right, so let me show you this simulation. All right, so there's the magnetic field, and we'll get this thing started. And you see what this is showing you is input power and output power. Okay, so this is output power, and so whatever work you did, the rate at which you did work is the rate at which you get electrical output. That's assuming frictionless rails. If there is friction between the rails, some of your input power will go and get transferred to heat, and then this electrical power would be, output power would be less. Okay. So for frictionless rails, the input power is equal to the output electrical output power. Okay. All right. So this slide shows you that the power output is, okay, so again, when you have an induced current in this loop, there's a magnetic force on the current, on a current carrying loop, and the magnetic force is in this direction. So to move this rod at constant velocity, you have to apply a force that's equal to the magnetic force. Okay, and the magnetic force is given by I times the length of the rod times B, the magnetic field. So that's the magnetic force. So you apply force times velocity is the input power, and it has to equal that. the magnetic force, and ILB, VLV was the induced EMF times I, and this is the output electrical power. Okay, so input power is equal to output power, and this is for a frictionless rail. Yeah. So again, Lenz's law tells you the direction of the current. So when you move this to the right, the way you figure out the direction of the current is in this direction, because flux is increasing in the area as you move to the right, and to decrease a flux, if the current flows in this direction, stick your right hand out. If your fingers are pointing in the direction of the current, the moment it's producing, this induced current is producing a magnetic field in the loop out of the page of the paper, and that's opposing the flux change. Okay, so the Lenz's law tells you the direction of the current. All right, so well, I'm going to pause here, give you guys a chance to ask questions, and then we'll look at some applications.